Let's share the screen. And we don't have initial conditions. So how to solve this? Here we don't guess. Here we do, sorry, here we do not guess the particular solution yp, since 1 over cosine squared x is not equal to something like a polynomial times exponential kx, or something like a cosine kx plus b cosine kx exponential ax. It is not of this form. So here, or some polynomial q of x, some polynomial, here it is a polynomial. So since it is not of these forms, 1 over cosine x, we definitely use the method of variation of constants or parameters. Okay, is that clear for you? So let's solve this problem. Y double prime plus y is equal to 1 over cos squared x. Let's first find the the homogeneous solution, then use the method of variation of constants. So here the characteristic homogeneous solution first. Solution. So we have the characteristic equation. We have k squared plus 1 is equal to 0. This leads that k squared is equal to minus 1, which is minus e squared. So k eventually is equal to plus or minus e. Okay, so eventually the solution would be, it contains the homogeneous solution. YH is C1 times cosine. Remember that this guy here is of the form alpha plus b eta, where alpha is equal to 0 and b is equal to 1. So it is exponential alpha x, which is 1, times c1 cos beta x, which is in this case 1, and so it is cos x, plus c2 times sine x. Okay, so this is the homogeneous homogeneous solution. Now we will try to look for the particular solution. So the particular solution assume that yp is equal to u1 function times cos x plus u2 times sine x. Okay, so this is the first solution, and this is the second homogeneous solution. So yp, as always, it is y1 u1 plus u2 y2. Okay, now we move on. Next, remember, I will not go through all the steps that we did before. That was only to explain to you the principle of variation of constants. Now we will simply apply it. So, by the method of variation of constants, we get, so u1 prime, as you remember, it was minus what? Minus, here I should remind you that this part, this guy here with the color red, this is actually equal to g of x. Okay, so it is minus g times what? Times the second solution all over the Wronskian, and u2 prime is actually equals to g times the first solution over w. Okay, and I must remind you that w, which is the Wronskian, is equal to y1 u2 prime minus u1 prime u2. Okay, now let's do the calculations. Let's do the calculations. Remember, let's write our let's write down our information. So remember that y1 is equal to cos x, and y2 is equal to sine x. So y1 prime is equal to minus sine x, and y2 prime is equal to cos x. Now w, the Wronskian, is equal to y1 times u2 prime. So this is the guy, and then next minus y1 prime minus u2, this guy here. So it is cos x squared minus, next we have minus sine x times sine x. So w actually is equal to cos squared x plus sine squared x, and this is actually equals to 1. Now you substitute. So please bear with me a little bit. I know it is too late, but this is the last time, so we must continue to finish the exercise. So y1 prime is equal to minus g y2 over 1, which is w. So here, what is the function g? The function g is 1 over cos squared x. So what we have here is minus 1 over cos squared x times y2. What is y2? This is sine x. So this is actually minus sine x over cos squared x. Sine over cos, what does it give you? It is minus tangent x over cosine x. So this is y1 prime. Now u2 prime. So this is y1 prime, u2 prime now. u2 prime is equal to g times y1 over 1, which is the, so it is 1 over cos squared x times y1, which is cos x. So actually we get y2 prime is equal to cos x. Okay. Now we should take the integrals to find y1 and y2. So y1 prime, yes. What? I didn't understand you, Rayla. Do you mean there is a mistake? Where? Yes. Ah, yes, 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 yes. Thank you. I got very tired and I didn't notice that. So it is 1 over cos x. Thank you again. So, sorry, I have to sip some water to continue. So, minus tangent x over cos x. So, u1 would be minus the integral of tangent x over cos x dx. And what is the integral of this function? Can you compute it? It is very easy. Minus, what is the tangent? It is actually sine x over cos, and we have cos, so it becomes something like this, dx. And I will not explain, since we did very much the integrals. You should check the previous chapter. So this is actually, when you integrate sine, it becomes, and we have here minus, it becomes we are integrating with respect to cos x over cos squared x. Okay, so if you put big X as cos small x, you would get that delta x, so delta x is actually equal to d cos x. So this is actually equal the integral of big X over x squared, which is equal to, so if you take the x to the numerator, it becomes x to the power minus 2. You integrate, it becomes to the power minus 1. So it becomes something like this, minus 1 over x to the power minus 1 here. And sorry, something like this. So this is actually, and you replace back, what you get, it is minus 1 over cos x. Okay, this function you may also it is called the secant. Okay, both are correct. If you write this or this, it is correct. So this is u1. Okay, is that clear? So I continue. Now we should take, we have u2 prime, let me change the color. u2 prime is equal to what? 1 over x. So u2 prime is equal to 1 over x. 1 over cosine x. So this implies that u1 is equal to the integral of dx over cosine x. And what is the integral of this function? Please remember to use the substitution. So let's do it so you remember the integration. This is a revision 2 to the integration. So put the change z is equal to tangent of x over 2. So this gives you that x is actually arc tangent of 2z, and this, sorry, 2z. So dx would be is equal to 1 over sorry, 1 over 1 plus, am I correct? Sorry, did mistake. So here in this part, so x here actually equals to what? If you take arc tangent z, then you multiply by 2, so it is 2 arc tangent z. So if you take the derivative of x, you will find here 2 over 1 plus z squared times d of z. Okay, is this correct? Okay, let's continue. Let me remind you that by this change of variable we have this rule here. This is the x over 2. Okay, so this part here is 2z, and this part here is 1 minus z squared. If you take, if you do the Pythagorean theorem, you will find that this part is equal to 1 plus z squared. And now you can deduce the that cos x would be equals to 1 minus z squared over 1 plus z squared, and sine x is equal to 2z over 1 plus z squared. Okay, so by this substitution, this integral will be equal to 1 over here, and we put the cos, which is 1 minus z squared over 1 plus z squared, and we substitute the dx by its value, which is 2 over 1 plus z squared dz. So now you simplify, this guy would be cancelled with this guy. What remains is 1 minus z squared, and we have the 2. I am not sure about this 2. You should verify the calculations. So the answer would be y1. So y1 is equal to the integral of dz, 2dz over 1 minus z squared. This is actually equal to the integral of dz of 1 minus z times 1 plus z. Now you use the technique that I have told you. So you should get something like this: a over 1 minus z plus b over 1 minus z is equal to that guy here, which is 1 over 1 minus z squared. If you do the calculations, you will get a minus az plus b, sorry, here we have plus, so a plus, so b minus bz all over that guy here. So you collect and a plus b now is equal to what? A plus b is equal to 1, and a minus b is equal to 0 since we don't have z. So the second a is equal to b, and you get here 2a is equal to a, so a is equal to 1 half and b also is equal to 1 half. So this would be equal to 1 half times the integral of dz over 1 minus z plus, so these two will go together, plus the integral of dz over 1 plus z. Okay, so now you know how to compute that. So eventually u1 is equal to ln 1 minus z plus ln, did I make any mistake? Sorry, please check the calculations. I always do mistakes when I compute. No, it is correct. So, and no. Check with me, please. Do I do these calculations are correct? So a over 1 minus z plus, if you do c, it is a plus a z plus b. So the sum is equal to 1 and a minus b is equal to 0. So a is equal to b. Okay. And we put that z is equal. So we return back. So we have, if you compute this, you will get something like this. It is ln and the multiplication 1 minus z times 1 plus z, and it is equal to ln 1 minus z squared. You return back, you will find that it is equal to ln 1 minus, what is z? Z is this guy here. Okay, it is tangent of x over 2 all squared. Okay, so this is the x. So you could simplify further. So here, sorry, yeah, let it like this. Let's let it only like this. So we find actually the general solution, which is this is sorry, this is u2, not u1. This is u2 actually. Here you have two u2, and here this is u2 and this is u2. So the particular solution yp is equal to u1 y1 plus u2 y2. now you substitute y1 by its value. So y1 is this guy here, minus 1 over cos x. So minus 1 over cos x, and u1, which is u1, it is cos x, plus u2 now, it is this guy, ln 1 plus tangent of x over 2 squared times u2, it is sine x. Sine x, okay. So you simplify, you will get the final answer is, so the general solution the general solution would be yg is equal to c1 cos x plus c2 sine x, and here we have minus 1 plus sine x times ln 1 plus tangent x over 2 all squared. So this is the solution to the equation y double prime minus y plus y is equal to 1 over cos squared x. Okay, so I think that that is it. If you are able, we can continue to problem 8 and 9. If you are tired, we stop here, and I will record the video only with myself and put it on the YouTube for you later. So what do you think? So Rayla, do you want to continue or stop here? Yes. So we stop. Yes. So we stop here. I will solve. So we stop here. I will solve the remaining exercises. I will explain during the solution, and I will put the recording of the video in the YouTube. I will send you the link in the classroom. You follow the link and you will find the solution of the next exercise, which is exercise 7, and the last exercise, which is exercise 8. Also, I will solve exercise number 5. I didn't put, we didn't yet uh, uh, I didn't yet solve the exercise number 5. You will I will upload the solution, and also I will maybe create the video for it and put it on the YouTube. So thank you for attending this course. Yes. Where exactly? uh, you too. uh, uh, in U2, if you add constants, it does not make any sense. Why? Because you are looking for a particular solution. We add constants when we are looking for the general solution. So in the particular solution, we only want to find one solution that we add to the homogeneous solution to get the general solution. So the general solution, let's look here. So here, uh, look here. This part here is the homogeneous solution, okay? And this part here, it is the particular solution. This part, when you substitute it, it will give you always 0. So this plus this is equal always to 0. Whatever, for any choice of C1 and C2, you will get it is equal to 0. But if you have initial conditions like y of 0 is equal to some y0 and y prime of 0 is equal to some say for example constant y0 prime, okay? Here if I gave you these two, you could find the specific values for C1 and C2. Okay, so this is the role of the homogeneous solution. The particular solution, however, it is what gives you this part here. It is y double prime plus y prime is equal to 1 over cos squared x. If then the general solution yg is equal both the homogeneous plus the particular. So the homogeneous will give you the 0 and the particular it will give you 1 over cos squared x. When your question is why when you integrate here why we don't here uh, here why we do not add c. The simple answer is we only look for one particular solution. We don't look for a family of solutions. And it suffices to take c equals to 0 to simplify the calculations. If you put c, it is correct, but it does not change anything, because the final answer that is required from the particular solution, it is to satisfy this part. So it does choose one value for c, and I choose c equals to 0 to simplify calculations. Is that answers the question? Yes, thank you. So if you don't have any other questions, we may stop. We can stop here. Anyone? Any other one have any other question? Okay, that's it. Thank you for attending till the exam. You have my email if you have any questions. Don't hesitate to send me any questions, and wish you good luck to the exam in the exam. Goodbye.